Hi. In the last video, we looked at the theory for sequences and series. We looked at arithmetic sequences, geometric sequences, sequences of higher order, and also some techniques of summation of sequences. In this video, we are going to apply those concepts in problems, and we'll start with a few questions which will cover all of those concepts. So let's look at the first one. This says, suppose each term of a sequence an is a distinct positive number, is a distinct positive number, and their reciprocals form an arithmetic sequence, So the reciprocals of the terms of an sequence form an arithmetic sequence. You have to find the value of a1 a2 plus a2 a3 and so on till a 2014 a 2015 divided by a1 into a 2015. You have to find the value of this expression. Okay, so we know here that the reciprocals of the sequence form an arithmetic sequence. So this is an AP. Let's say that its common difference is D. Common difference is D. So that means that 1 by A2 minus 1 by A1 is equal to 1 by A3 minus 1 by A2 is equal to 1 by A 2015 minus 1 by A 2014 is equal to D, right? Because 1 by an forms an AP, therefore this relation is true, which implies that we can write it as A1 minus A2 by A1 A2 is equal to A3 minus A2 by A2 A3 and so on till A 2014 minus A 2015 by A 2014 A 2015 is equal to D, right? We have this relation. Now, a simple property of ratios that you should be aware of is this: x1 by y1 is equal to x2 by y2 is equal to x3 by y3. Then you can also say that it will be equal to, let's say, x1 plus x2 plus x3 by y1 plus y2 plus y3. You can prove this property of ratios. As long as you have certain things in ratio, that whole ratio will also be equal to the sum of the numerators by the sum of the denominators. Try proving this yourself. It is very easy to prove. So we will use this property now and we'll apply it to these fractions, right? So you can see that this is my x1 and this is my y1, this is x2, y2 and so on till xn, yn. So this should be equal to a1 minus a2 plus a2 minus, actually this should be a2 minus a3. If you notice here, I have made a mistake. This should be a2 minus a3. So I have here a2 minus a3 plus so on till a 2014 minus a 2015. I'm adding all the numerators and denominator is simply the addition a1 a2 plus a2 a3 so on till a 2014 a 2015, right? So this becomes, you can see it's like a telescoping series. All of these terms get cancelled and you have a1 minus a 2015 by this denominator, right? So I'll write it on the next screen. What I have so far is a1 minus a 2015 by A1, A2 plus A2, A3 till A2014, A2015 is equal to D. Why is it equal to D? Because each of those ratios was equal to D. Each of those ratios was what? D, right? We had written that earlier. These were all equal to D because this is the difference of 1 by A2 minus 1 by A1, and this is 1 by A3 minus 1 by A2, right? So we have this relation. The first half of this equality is true, right? Okay. Now, since 1 by an is an arithmetic sequence or arithmetic progression, we can therefore say that 1 by A2015 is equal to 1 by A1 plus 2014D. This is the 2015th term and this is the first term. So we can write the AP rule and we have this equation which implies that A1 minus A2015 by A1 into A2015 is equal to 2014D. Right? Correct. So what we get here is A1 minus A2015 is equal to 2014D multiplied by A1 A2015, right? Correct. Now, from here we can basically say that A1 into A2015 is equal to A1 minus A2015 by 2014D, right? Okay. And now from this first relation, from this relation, we can say that A1, A2 plus A2, A3 plus A2014, A2015 is equal to A1 minus A2015 by D, right? And now I have this result and I have this result. And if I divide the two, you will get A1, A2 plus A2, A3 plus A2014, A2015 divided by A1, A2015 is equal to A1 minus A2015 by D divided by A1 minus A2015 by 2014D. So this factor gets cancelled, D gets cancelled, and you have the answer 2014. So ultimately, it was an easy question. It is just a little bit of manipulation and the ratio property that we used intelligently. So you can realize that if you have x1 by y1 is equal to x2 by y2 and so on till xn by yn, it is equal to x1 plus x2 plus xn by y1 plus y2 till yn. And if you use that along with our result that 1 by an forms an AP, you can basically solve this problem pretty easily, right? Let's look at the next one. This is question number 2. Let the sum of first n terms of a geometric sequence an be Sn. Suppose S of 10 is 10 and S of 30 is 70. You have to find S of 40. It's a very simple question. We know formulas for geometric sequence sum of terms till n. So we can do it pretty easily in a standard way. I'll just outline the solution for you. We can denote B1 is equal to S of 10, B2 is equal to S of 20 minus S of 10, B3 is equal to S of 30 minus S of 20, and B4 is equal to S of 40 minus S of 30. You will see the advantage of doing this. So you will realize that if Q is the common ratio of the sequence AN, then B1, B2, B3, and B4 form a geometric sequence, with common ratio Q power 10, with common ratio equal to Q power 10. How do we know this? You can confirm this easily. Think about B1. What is B1? B1 is the sum of the first 10 terms. So it will be B1 is equal to A1, 1 minus Q power 10 by 1 minus Q, right? And similarly, B2. B2 is the sum of the first 20 terms minus the sum of the first 10 terms. So it will be the first term of this will be the 11th term of the original sequence, right? 11th term. So it will be A1 Q power 10 is the first term, and then it is 1 minus Q power 10 by 1 minus Q, because the common ratio is the same. And similarly, you will be able to, can you see that B1 and B2, the ratio is Q power 10. You can confirm similarly B3 and B4 will be, B3 will be B2 into Q power 10 and B4 will be B3 into Q power 10. So we have this nice relation that B1, B2, B3, B4 form a geometric sequence with common ratio Q power 10. And now we know from the problem that S10 is equal to 10. So B1 is equal to S10 is equal to 10, and S30 is actually equal to, if you think about it, what is S30? B1 plus B2 plus B3. If you add B1, B2, B3, S10 gets cancelled, S20 gets cancelled, and you're left with S30, right? So S30 is B1 plus B2 plus B3, and that is equal to 70, right? So that must be equal to B1 1 plus, it is actually Q power 10 plus Q power 20, right? This is equal to 70. And we know B1 is 10. So we have 1 plus Q power 10 plus Q power 20 is equal to 7, right? So this is pretty easy. You take Q power 10 as R, so it will become R square plus R plus 1 is equal to 7, where R is equal to Q power 10 for us, right? And you will be able to solve this. This is a quadratic, simple quadratic. You will get R is either 2 or minus 3, right? And since we want positive terms here, since R is a power, it cannot be negative. So 2 is equal to Q power 10 we are getting. And therefore, S40 is being asked here. That should be, if you think about it, B1 plus B2 plus B3 plus B4 is S40, right? B1 plus B2 plus B3 plus B4. Now, B1 was 10 and the common ratio of the B sequence is 2 because Q power 10 is 2. So S40 is simply 10 plus 20 plus 40 plus 80, right? So this becomes basically 70 plus 80 is 150. Obviously, there are other ways to do it, but this is the fastest way because you are spotting the pattern that the S10 and the S20 minus S10, B1, B2, B3, B4 sequence has a common ratio of Q power 10 if Q was the common ratio of the original geometric sequence, right? Okay, let's move on to slightly more interesting questions. Question number 3. Question number 3 says, suppose an arithmetic sequence AN of order 2 satisfies A2 minus A1 is equal to 110 and the sum S11 of the first 11 terms of the first order difference sequence Bn is the maximal number. Okay, assume that when S11 is maximum, the maximum value of An is 2017. Find the general term of An. So this question uses concepts of higher order sequences. And when we say arithmetic An is an arithmetic sequence of order 2, that means the difference sequence Bn. What is difference sequence? An is the sequence like this: A1, A2, A3, A4, and so on. The difference sequence is Bn, which is A2 minus A1, A3 minus A2, A4 minus A3, and so on. If An is a arithmetic sequence of order 2, then Bn is an arithmetic sequence of order 1, right? Or basically an arithmetic sequence of order 1 is a standard arithmetic sequence or an AP. So Bn is an AP, An is a higher order arithmetic sequence, right? In the question he has said that A2 minus A1 is 110, right? So the first term of Bn is a simple arithmetic sequence of order 1, and B1, the first term of Bn is A2 minus A1 is 110, right? Okay, let the common difference of Bn be D, right? Then what we know is that B11 would be what? B11 would be 110 plus 10D, right? Correct. And what is B12? B12 is 110 plus 11D, right? Now think about it. Bn is an arithmetic sequence, and the question is saying that sum S11 of first 11 terms of the Bn sequence is the maximal number. It is the maximum number, sum to 11 terms. So if it is a regular arithmetic sequence which is increasing in nature, we should realize that B12 should be bigger than B11, right? Because sum till 12 terms should be greater than sum till 11 if it was an increasing sequence, because you are constantly adding terms. So the only way that sum to 11 terms can be maximum is if it was a decreasing sequence and the 12th term was negative. B12 is less than 0. If B12 is less than 0 and B11 is greater than 0, right? Then we can say for sure that the sum to 11 terms is maximal. I hope you are understanding what I'm saying. If you add up some terms and it was a decreasing sequence, then all the positive terms will get added, and if it is still 11 terms or positive, then that sum till 11 terms will be maximum. And after that, if you take the next term, the sum will start declining, right? So basically, this statement here that sum S11 of Bn's 11 terms is maximal means that B11 is positive, whereas B12 is negative, right? Now, from these two inequalities, we can say that 110 plus 10d is greater than 0. So that means 11 plus d is greater than 0. And that means d is greater than equal to minus 11. And from here, we can say 10 plus d is less than 0. So d is less than equal to minus 10, right? Both these results must be true. So d has two choices. It can be minus 11 or minus 10. And the next part of the question tells us we have minus 11 is less than d is less than equal to minus 10. These are our options. The next part of the question says that assume that when S11 is maximum, when this is true, the maximum value of AN is 2017. The maximum possible value of AN will happen if the common difference of this, we take the common difference as high as possible. So right now, common difference could be minus 11 or minus 10. So we should take the higher value to get the maximum value of AN, right? So we'll assume that common difference D is minus 10 instead of minus 11 because we want to get the maximum possible value of AN here, right? Okay, so now we have assumed that when S11 is a maximum value, D is equal to minus 10. And we already know that B1 was 110, right? So that means we can find out S11. S11 will be equal to 11 by 2, n by 2, twice of B1 plus 11 minus 1, 10 times D, right? So this will become basically 11 by 2 into 220 minus 100, and that is equal to 660. S11 is coming out to be 660. Also, for the original sequence, AN plus 1 can be written as A1 plus A2 minus A1 plus A3 minus A2 plus so on till AN plus 1 minus AN. Notice that this is a nice trick. We are writing the n plus 1th term using the first term and then combination of terms which are differences of two successive terms. We are splitting these terms. And by telescoping method, you can realize that A1 can be cancelled here, A2 can be cancelled here, and you will be left with just AN plus 1. However, this is useful because we can write it as A1 plus, this is B1, right? This is the difference of the first two terms. This is B2, and so on till this is Bn. So these are the first n terms of the Bn sequence. So that is equal to A1 plus Sn, right? We are getting An plus 1 is equal to A1 plus Sn. So when Sn is maximum, that implies that time An plus 1 is maximum, right? So An plus 1's maximum value will be A1 plus, let's say n was 11. So S11 is maximum value. We know S11 was 660, right? So we can say that AN plus 1 maximum is A1 plus 660, and this maximum value of AN plus 1 was given as 2017, right? In the problem itself, it was given that the maximum value of An plus 1 was 2017. So that means A1 plus 660, A1 should be equal to 1357, right? Yeah. 1357 is the value of A1 here. What are we doing here? We are saying that an plus 1 could be written as a1 plus sn, and when sn is maximum, that is 660 is the value, then an plus 1's maximum term must be 2017, right? That was given in the problem. So from here we are able to deduce that a1 is 1357. And now we'll just find the general term of this an sequence. That is pretty simple because we have an plus 1 is equal to a1 plus sn. And what was Sn? If you notice, Sn was n by 2, 2b1 plus n minus 1 into d, right? So this becomes a1 plus n by 2, 2b1 plus n minus 1 into d. And this is an plus 1. And now we have, this is 1357 plus n by 2. And this is 2b1 is 2 into 110 plus n minus 1 into minus 10, right? So this simplifies out to become minus 5n square plus 115n plus 1357. That is your an plus 1. And once we have an plus 1, we can find an by replacing everywhere n has to be replaced with n minus 1. And when you do that, you will realize that it is minus 5n square plus 125n plus 1237. That becomes your quadratic term, which denotes the general term of the an sequence. So notice how we have understood the problem. The first thing we noticed was the an sequence is order 2 arithmetic sequence. So bn sequence is a simple AP. And we understood that bn must be a decreasing AP because sum to 11 terms was maximal, right? So sum to 12 terms was less than sum to 11 terms. So from there, we figured out the common ratio. Common ratio had a range, and we took the higher value. And because the maximum value term of an sequence was 2017, so that any term of an sequence could be written as a1 plus sn, and we found out a1 because the maximum value of sn was 660. So we got the maximum value of an plus 1 term was 2017, so we found a1 from there, which came as 1357. Once you know 1357, we are using this condition again. The key thing to remember here is the way we split the terms. an plus 1 was a1 plus a2 minus a1 plus a3 minus a2. This technique we'll see many times, okay? So this is important because this was written as a1 plus b1 plus b2 till bn. Okay? And this became your Sn of the difference sequence. This is the sum to n terms of the difference sequence. And basically you're saying that for any arithmetic sequence of higher order, you can write the n plus 1th term as a1 plus the sum to n terms of the difference sequence. That is something that you should keep in mind. Let's look at the next problem. This is slightly easier. We have question 4. Let every term of second order difference sequence of an be 16 and a63 is equal to a89 is equal to 10. You have to find a51. The question is pretty simple. You have every term of a difference sequence being 16, and this is the second order difference sequence, right? The second order difference sequence of an is 16. So we know from the theory session yesterday and the previous class that if it is a second order difference sequence, then an is a polynomial of degree 2 in n. Polynomial of degree 2 in n, right? because the second order difference sequence of this an is a non-constant, non-zero constant sequence, right? There is a property that we discussed in the previous class that if the pth order difference sequence is a non-zero constant sequence, then the original sequence is a pth order sequence. So it will be a polynomial of degree p in n, right? So that means that we can write an as a quadratic of order 2. An can be written as a quadratic of degree 2, and we already know that a63 is equal to a89 is equal to 10. So the values of the quadratic for n is equal to 63 and n is equal to 89 are matching. So in general, the quadratic can be written as some constant times n minus 63, n minus 89 plus 10, right? This captures all this information, right? Because when you put 63 and 89, this part vanishes and it becomes equal to 10. And other values, obviously, you will get other values, right? So now what we can say is that this is my an, and we have, let's say we write the terms a1, a2, a3, a4, and so on. The first order difference sequence will be what? a2 minus a1, a3 minus a2, and a4 minus a3, and so on. And the second order difference sequence will be 16, 16, 16. That is what is given in the problem. So what this means for us is that the difference of this and this is 16, right? So we know a3 minus a2 minus a2 minus a1 is equal to 16. So that means that we have a1 plus a3 minus 2a2 is equal to 16, right? Since the second order difference sequence is 16, we are just saying that a1 plus a3 minus 2a2 is 16. And if I put this data in this relation for an, I will get the value of capital A. How? We can say that a1 plus a3 minus 2a2 is equal to 16, and an was a times n minus 63, n minus 89 plus 10. So what is a1? a1 is 1, a into 1 minus 63, 1 minus 89 plus 10. a3 is a into 3 minus 63, 3 minus 89 plus 10. And a2 is a into 2 minus 63, 2 minus 89 plus 10. If you just solve this, you will be able to get the value of a. And the a value comes out to be 8. You can just solve this and get a value as 8, which gives us an is equal to 8 times n minus 63, n minus 89 plus 10. And now you can find a51. a51 will be 8 times 8 minus 63, 8 minus 89 plus 10. And that comes out to be 3658. You can check the calculations yourself. I just wanted to show you how you approach this problem. Okay. The next one that we'll look at is this one. We have to find the sum of this series. Find the sum of Sn is equal to 1 into 3 into 2 square plus 2 into 4 into 3 square plus so on, n into n plus 2 into n plus 1 squared. Many times in problems of summation in this section on this chapter, what you need to do is to employ the method of differences where you express the general term as a difference of two terms. So here we'll look at this general term or write it in terms of k plus 2, k plus 1 whole square can be written as k plus 1 k plus 2. And if you think about it, the second k plus 1 is k plus 3 minus k plus 3 minus 2, right? Yeah. The second k plus 1 here is k plus 3 minus 2. So this can be written as k plus 1, k plus 2, k plus 3 minus 2k, k plus 1, k plus 2, right? Correct. So this summation is basically two separate summations, right? We'll look at these separately, and again we'll employ method of differences. So let's call this capital Kn and let's call it Tn. I want to find capital Kn, which is summation from 1 to n of k plus 1, k plus 2, k plus 3. Now the way we split this one is we write it as, think about it, this term here, right? We can write it as k plus 1. This term we can write it as k plus 1, k plus 2, k plus 3, and we multiply a k plus 4 here, and then we subtract k minus 1, k plus 1, k plus 2, and k plus 3. Think about this. We have multiplied a higher term here, k plus 4, and multiplied a lower term here, k minus 1. What is the advantage? We could take all of the remaining 4 terms as common, right? And you would get k plus 4 minus k minus 1, which is actually simply 5, right? So the answer that you will get here is 5 times this. So we will put a 1 by 5 outside. Do you understand what we have done? We have written this term, general term, as 1/5 of this minus this. You can easily see that the 4 middle terms get taken as common, and the last term here and the subtraction of this is 5, which cancels the outside 5. Why is this good? Because these are 5 successive terms, and these are also 5 successive terms. The only difference is the starting points and ending points are different. This starts from k to k plus 4, and this from k minus 1 to k plus 3. So the point is that now when we do the summation here over k, it will become telescoping series, because you start by putting 1. When you put 1, you get here 1, 2, 3, 4, 5, and here you get 0. When you put 2, you get 2, 3, 4, 5, 6 minus 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 here gets cancelled with the first terms 1, 2, 3, 4, 5. And basically, you can evaluate it yourself. The sum of Kn will be basically 1 by 5 n into n plus 1, n plus 2, n plus 3, and n plus 4. This is by telescoping series method. Since we are able to split the Kn general term into 2 separate sequence of 5 factors, right, which are very similar to each other, right, we'll apply the same process for finding Tn. So if you recall, we had to evaluate the value of this series. Tn was equal to the sum of 2k, k plus 1, k plus 2, and k goes from 1 to n. So we take the 2 outside and we follow the same exact process, right? So we will say twice of summation k is equal to 1 to n, k plus 1, k plus 2. And now how do I split this? I'll write it as k plus 1, k plus 2, k plus 3 minus k minus 1, k plus 1, k plus 2. And if you think about it, you can take these 3 terms and these 3 terms common and it becomes 4. So we will do a 1 by 4 outside. And the 2 is a constant outside. So now this 1 by 4 comes outside, becomes a half. And this is a simple summation. This is a sequence of 4 terms. We are using the same trick again. You will realize that this Tn will come out to be basically half n, n plus 1, n plus 2, and n plus 3. And then finally, you have to do Kn minus Tn, right? Or do we have to do Kn plus, you have to do Kn minus Tn. Because earlier we had written the initial thing as the difference of Kn and Tn, and you should be able to calculate the answer. The final answer I'm writing, you should work out the steps yourself. Sn is 1 by 10 n, n plus 1, n plus 2, n plus 3, and 2n plus 3. So this question denotes the technique, or shows you the technique of basically the method of differences, where we split terms and we do summations in that way, right? We will see more problems of that, but before that, let's look at this one. Let's look at this question. We have assume that the sequence of integers an satisfies the following conditions. Satisfies the conditions. First condition is a of n plus 2 is equal to 3 times a of n plus 1 minus 3 times a of n plus a of n minus 1 for n belonging to 2, 3, 4, and so on. Second condition is twice of a2 is equal to a1 plus a3 minus 2. Third condition is a5 minus a4 is equal to 9. And fourth condition is a1 is equal to 1. You have to find Sn for the sequence an. You have to find the sum of n terms of this sequence, right? Okay. So let's think about it. These are the things that are given to us. So let's say that we write the difference sequence Bn as an plus 1 minus an, and we write Cn as the second order difference. So it is Bn plus 1 minus Bn, right? We are defining these two sequences. So we can say Cn is equal to Bn plus 1 minus Bn is equal to, if you write Bn plus 1, it will be An plus 2 minus An plus 1 minus Bn is An plus 1 minus An. So this becomes equal to An plus 2 minus 2 times An plus 1 plus An. So the second order difference Cn is equal to this, right? An plus 2 minus 2 times An plus 1 plus An, right? Now, think about it. This looks very similar to this first result, or at least it looks a little similar, right? So we will use this first result An plus 2 here. So if I use An plus 2 from the first result here, I should get something for Cn. I will do that on the next screen. So I will say Cn was equal to, we wrote An plus 2 minus 2 times An plus 1 plus An. And the first condition was telling us as An plus 2 was equal to 3 times An plus 1 minus 3An plus An plus minus 1, right? Correct. So using that, we are getting Cn is equal to 3An plus 1 minus 3An plus A of n minus 1 minus 2An plus 1 plus An, right? So this becomes Cn is equal to A of n plus 1 minus 2An plus A of n minus 1, right? And using the third result, not the third result actually. Looking at this and looking at this, you should see that there are some similarities here, right? Here we have n plus 1, here n plus 2, here n plus 1, and here n minus 1 n. So this implies that this stuff is basically C of n minus 1, right? If you see this condition, from here C of n minus 1 would have been this. And we are basically getting Cn is equal to C of n minus 1, right? So Cn is a constant sequence. And Cn is a constant sequence means the second order difference sequence is constant. That means our original sequence is an order 2 sequence, and Bn sequence is a simple arithmetic progression, because it is Bn sequence must be order 1 now, right? Correct. So now what we will do is look at condition 2 of the problem, which says 2a2 is equal to a1 plus a3 minus 2. And from here, we can say that from here, what is C2? C2 was equal to a C2 was equal to a4. Okay, actually what we can say is C1. Put n is equal to 1 here. C1 is equal to a3 minus 2a2 plus a1, right? So a1 plus a3 minus 2a2. So what we are getting is a1 plus a3 minus 2a2 is equal to C1, right? And here we have 2 is equal to a1 plus a3 minus 2a2. So this is equal to C1. So therefore we are getting C1 is equal to 2. And since Cn is equal to Cn minus 1, Cn is coming out as a constant sequence 2, right? Great. So that means Bn has common difference equal to 2, right? We know that now, because the constant sequence Cn is 2, 2, 2, 2, 2, right? So the Bn, the first order difference sequence, is an AP of common ratio 2. Now we do the same process as we have done several times before. An is a1 plus a2 minus a1 plus a3 minus a2, so on till a n minus a n minus 1, right? So we can say that this is a1 plus summation of k goes from 1 to n minus 1 bk, right? Because d of n minus 1 is an minus an minus 1, right? Now this is my an, so we get this summation. We know that bk is an arithmetic sequence of common difference 2, because the Cn sequence was a constant sequence of 2, right? So therefore the summation of bk can be done by the formula for summation of arithmetic progression. This is n minus 1 by 2 b1 plus b1 plus n minus 1 minus 1 n minus 2 into 2, right? So what we are getting here, after simplifying, an is equal to a1 plus n minus 1 b1 plus n minus 1 into n minus 2. After simplification, this was an, right? And the question has already given us the value of a1 as 1. That was the fourth condition in the problem. So we now know an is equal to 1 plus n minus 1 b1 plus n minus 1 into n minus 2. And we also know that a5 minus a4 is equal to 9. And this is basically b4, right? This is b4. This is the fourth term in the first order difference sequence. But b4 can be written as b1 plus 3 times d, which is 2. So it is b1 plus 6 is b4. So b1 is equal to b4 minus 6, and since b4 is 9, b1 is 3, right? So now we have found b1 also. So an is coming out to be 1 plus 3 times n minus 1 plus n minus 1 into n minus 2, right? And now you can just simplify this. N minus 1 common, it will be n minus 2 plus 3, which is n plus 1. So this is becoming 1 plus n square minus 1. And finally, you are getting an is n square. You are getting, after simplifying, an is n square. So the sum to n terms of this is n plus 1 to n plus 1 by 6. So very nice question. There is enough information to solve for everything that we need. You just need to follow the steps, go through it yourself, try these questions yourself, and once you have gotten the hang of it, you will be able to understand how we are getting this, right? Let's look at the next problem. Question 6. This question, we have to find the sum summation of n goes from 1 to 2015 minus 1 power n square plus n plus 1 by n factorial. Okay, so now we can say for n belongs to natural numbers, n square plus n plus 1 by n factorial can be written as n square plus by n factorial plus n plus 1 by n factorial, and that can be written as basically n plus 1 by n factorial plus n by n minus 1 factorial, because one n can get cancelled here in this term, right? So we have this situation. Notice that there is a nice pattern here, n plus 1 by n factorial and n by n minus 1 factorial. Both of the terms are having a similar form. The numerator is 1 more than the denominator, right? However, what we need is minus 1 power n of n square plus n plus 1 by n factorial. So what we will say is this is minus 1 power n plus 1 by n factorial plus minus 1 power n by n minus 1 factorial, right? Now what we'll do here is we'll do a trick that will help us do the summation easily. What is the trick? Notice that if n is even or odd, this sign will be same, right? Minus 1 power n and minus 1 power n will have the same sign. But what we want is to have opposite signs here. So what we'll do is this, minus 1 power n, we'll keep the first term as it is, and we'll write it as minus into minus 1 power n minus 1 n by n minus 1 factorial. Notice that this is the same thing as this. We have just taken a minus sign and converted this plus to a minus, right? What is the advantage of this? The advantage of this is now the first term and the second term will always have opposite signs, right? Why is that good? Because when you do telescoping series, when you try to do the summation till 2015 of this, it will be good to have opposite signs because the terms will keep getting cancelled now. So let's do the telescoping series. Minus 1 power n minus 1 n by, here there was no factorial here, n by n minus 1 factorial. If you add these two terms, let's write a few terms and see. The first term will be when n is 1, it will be minus of 1 into 2 by 1 factorial minus of minus 1 power 0 is 1 and 1 by 0 factorial. This is the first term. The second term is when n is 2, it will be 1 into 3 by 2 factorial minus of minus 1 power n is 2. So it is 1 and 2 by 1 factorial, right? So notice that there is a plus 1 into 2 by 1 factorial, and there was a minus 1 into 2 by 1 factorial here. So this term gets cancelled with this term. Similarly, this term will get cancelled with the next term. So you should evaluate this telescoping series now. The main idea here was to write it in a similar form first. What is the similarity in the form? The numerator is 1 bigger than the denominator, and both cases the factorial is coming in the denominator, right? So the terms had a similar form, and all we needed was the sign to be interchanged. So in one of them, we keep the sign minus 1 power n, and in the other one, we take a minus 1 out, and basically get minus of minus 1 power n minus 1, right? You should do the telescoping sum yourself. The answer I will write here. You can verify this. Answer should be minus 2016 by 2015 factorial minus 1. Okay. For the next problem, we'll look at this one. A sequence xn is defined as x1 is equal to half and xn is equal to 2n minus 3 by 2n multiplied by x of n minus 1 for n is equal to 2, 3 and so on. We have to prove that x1 plus x2 plus xn is less than 1 for any positive integer n. Positive integer n. Now, basically from the definition itself, x1 is 1 by 2, and xn is a positive number multiplied by previous term. So it will be positive. So we can say that xn is positive for any n belongs to natural number. That is obvious from the way the sequence has been defined. Now we can say that xk is equal to 2k minus 3 by 2k multiplied by xk minus 1, and we can rewrite it as 2k xk is equal to 2k minus 3 times xk minus 1, and we can write this. We want one single xk here, so we can write it as xk plus 2k minus 1 xk is equal to 2k minus 3 xk minus 1, and now we can rewrite it as xk is equal to 2k minus 1 minus 3 xk minus 1 minus 2k minus 1 xk, right? So basically we have taken this second term here to the left, to the right hand side. We are writing xk in terms of xk minus 1 and xk, right? Now we will use this condition. So let's try to do this summation. We have to find summation of k goes from 1 to n xk, right? So we can say that that is equal to x1 plus summation of k goes from 2 to n xk, right? That's the same thing, but we are starting from 2 because our original relation was valid for n is equal to 2 onwards, right? But now we will rewrite this as k is equal to 2 to n. Instead of xk, we will write it as 2k minus 3 xk minus 1 minus 2k minus 1 xk. We can do that because we have proved that xk was equal to this based on the initial condition of the problem, right? So now let's look at this. This should become a telescoping series. So let's see first few terms. When you put k is equal to 2 here, you will get 1 into x1 minus k is equal to 2 here, so this is 3 times x2. This is the first term. Then you put k is equal to 3 here, it will be 6 minus 3, so 3 into x2 minus k is equal to 3, so 5x3, right? And the next term would be k is equal to 4, you will get 8 minus 3, so 5x3 minus 7x4, right? So you can see easily the pattern. This is getting cancelled. This is a clear telescoping series. So once you do the sum from 2 to n, you will get basically x1 plus, inside you will get x1 minus 2n minus 1 xn. So basically what we are getting is summation of k is equal to 1 to n xk is equal to 2x1 minus 2n minus 1 xn, right? And in the problem itself, we know that x1 is half, so 2x1 is 1 minus 2n minus 1 xn. And since xn is greater than 0, we are getting that summation xk from 1 to n is less than 1. This summation is coming 1 minus something, no? And this something is positive. So therefore, we have proved that the summation of the first n terms of this sequence is less than 1, right? Okay, let's look at another problem. Right. This will be the last problem that we will discuss. Hope you have gotten the idea of how we solve these sequence and series questions. We have seen most of the techniques by now. Let's look at one last problem. Suppose that a given sequence xn satisfies x1 is greater than 0 and x of n plus 1 is equal to root 5 xn plus twice of root over xn square plus 1 for n belongs to natural numbers. We have to prove that among x1, x2 till x 2016, there exist at least 672 irrational numbers. So we have to prove that among the first 2016 terms, there are 672 irrational numbers, right? Okay. Fine. So we have this condition here, xn plus 1 is equal to root 5 xn plus 2 root over xn square plus 1. We can rewrite this as xn plus 1 minus root 5 xn is equal to 2 times root over xn square plus 1. And if we square this on both sides, we'll get xn plus 1 whole square plus 5xn square minus 2 root 5 xn into xn plus 1 is equal to 4 times xn square plus 4, right? After squaring. So we bring everything to one side, we are getting xn plus 1 whole square plus xn square minus 2 root 5 xn into xn plus 1 is equal to 4. This is the condition that we are getting so far, right? So using this condition, if we replace in this condition, we replace n with n plus 1. What am I saying? I'm saying that since this condition is true for all natural numbers, because the original condition here is true for all natural numbers. Once we have this condition, we can replace n with the higher number. So we can say xn plus 2 whole square. Instead of n, we are putting n plus 1. So this should also be true. Minus 2 root 5 xn plus 1 xn plus 2 is equal to 4, right? Okay, so we have two similar looking conditions. If I subtract now, I will get xn plus 2 whole square minus xn square, and this gets cancelled, and we get minus 2 root 5 xn plus 1 common, and we have xn plus 2 minus xn is equal to 0. This is coming by subtracting this minus this, right? So we can say xn plus 2 minus xn common here, and we'll have xn plus 2 plus xn plus 2 root 5 xn plus 1. No, not plus. I think we get a minus 2 root 5 xn. I'm just taking common. You have to do it correctly. This plus xn minus this, right? This is the condition that we are getting. Now, obviously, this is not a constant sequence. So xn plus 2 is not equal to xn. So the first factor cannot be 0, right? So the second factor must be 0, correct? So if the second factor is 0, let's rewrite that on the next screen. We get xn plus 2 plus xn minus 2 root 5 xn plus 1 is equal to 0. So that implies that xn plus 2 plus xn by xn plus 1 is equal to 2 root 5, right? This is the condition that we are getting for the sequence. Now think of this, these are three successive terms. This tells us that among the three consecutive terms, xn, xn plus 1 and xn plus 2, at least one term must be irrational. Why should it be irrational? Because if all the three terms were rational, the ratio of this can never be irrational 2 root 5, right? Between any three consecutive terms, at least one of them has to be irrational. So only then can this come out to be 2 root 5, which is irrational, right? So that means that out of the first 2016 terms, 1 out of 3, we should have at least 2016 by 3, right? Irrational terms. And 2016 by 3 is basically 672. The number of irrational terms could be more, but at least 672 of them are definitely irrational, right? So basically a simple proof, but it is only obvious if you simplify your original sequence relationship and get this condition. Xn plus 2 plus xn minus 2 root 5 xn plus 1 is 0, right? Okay, so we looked at several problems. We looked at normal arithmetic sequences, summations, higher order sequences, and also some summation problems. So hopefully you have gotten a good exposure to all of these kinds of ideas, and you will be able to use them in your own problems. The next topic and the next sequence of lectures that we'll do will go in a slightly different direction. We'll look at a little bit of coordinate geometry. It is not a major topic in Olympiads, but sometimes you might have problems where you need some geometry and some Cartesian geometry. So we'll look at circles, straight lines, and conic sections in the next few sessions. So stay tuned for that, and I'll see you in the next class.